Hello. We're going to try a problem that now uses air resistance that actually takes air drag into consideration. And we're actually going to compare this with case for free fall. So as you can tell here, I have two free body diagrams. One where the air resistance or air drag has already overcome the weight of the raindrop. Would you expect that this is a zoomed in picture so that we expect the weight and the mass of a raindrop to be very, very, very small. And so it doesn't take long for air resistance to overcome as soon as it precipitates. But for free fall, that does not happen. So it's just something that accelerates and accelerates and accelerates. By how much? By exactly, at least here on Earth, 9.8 meters per second squared. So you can kind of see which one you think will be faster, which one you think will be slower, but I'm going to leave the spoilers for our answers. So we're going to solve the case of which one's going to be faster, terminal velocity or the final velocity for free fall. Notice I already have the formula for terminal velocity right here. We'll also need the formula for weight or force due to gravity. Drag coefficient is something that's given. And this symbol here, rho, is actually the density of the air that the airdrop is falling. Even though we're already given the density of water, we'll need that for something else. And this area is actually something special here. It's actually the cross-sectional area taken perpendicular to the relative velocity. So whatever area is, we're assuming this to be a sphere, so the cross-sectional area is a circle. Okay, so the area here, I'm just going to go ahead and write that down. It's just going to be simply pi r squared. Okay, so I've gotten a little bit ahead of myself. So I'm going to go ahead and write the given for this. I'm going to write the formulas on the bottom because I'm running out of space. First, we're given the radius already, and it's in millimeters. I advise that you actually convert all the units to SI before you calculate, so it actually reduces the possibility of getting conversion errors in your calculations. This is just me. I like to do things all early on and just do the numbers later. And next we're given the height, which actually is our y initial at 1200 meters. I actually think this is pretty low. I think rain, if I listen to my weatherman correctly, it happens like tens of thousands of meters or feet above. That would be tens of thousands of feet above the ground. Drag coefficient is something special for this case, in this case alone, so it's 0.60. We're also given the density of water. This is actually the density of pure water. And for rainwater, it actually is a lot more pure than what we find in our taps and our faucets at home. And the density of the air for this 1200 meters is assumed to be 1.2 kilogram per cubic meters, which is, if you notice, is actually much less than density of water. Right? That makes sense. Okay, formulas. I already have two up there. I'm going to rewrite them down here as well before I forget. Okay, the formula for terminal velocity. And then I'm going to double check. That's air, and this is cross-section area. That's a circle. Boom. CPA. It's actually a row. We're also going to need the formula for volume of a sphere. We're assuming that all rain droplets are spheres. It's not a teardrop as what you would see in cartoons. We'll also need the formula for density. Density of the water, it's going to be mass over volume. Already the formula for area as well of a circle, and a formula for weight, or the magnitude of the weight. We know it's going down. Okay. Also, and this is for the part B, the free fall part, we're going to need this formula. It's a kinematics equation, which hopefully you are familiar with by this time, but if not, Here it is. To compare, remember we're trying to compare terminal velocity with this, and as a matter of fact, let's go ahead and assume that the initial velocity is going to be 0, so that cancels out, and I'm just going to save this for later. It's going to be square root of 2g delta y. Whoops, negative. We'll find out how that works out later. So I'm going to solve first for the volume. That's what I have here on my solution sheet. And remember that I already converted this to meters. So when I get my volume, it's already going to give me meters cubed. I don't have to worry about the powers of 10. And I already have the answer here. We expect something quite small for 1.5 millimeters. And sure enough, it's times 10 to the negative 8 in orders of magnitude and cubic meters. Okay, we're going to use this in formula for that looks like a sigma. Formula for density, but we are going to solve for the mass. Okay, and so that gives us mass is density, in this case density of the rainwater, times the volume that I just got. That's just a circle or a sphere. Okay, times the number that I just calculated. Okay, notice that cancels out because we are indeed looking for mass. Okay, and this gives us a number not too much different from our volume, but smaller in terms of magnitude. That's a 5. And there we go. We expect the mass of this to be small as well. Now I can use that to solve for my, use capital M, let's be consistent. Okay, and just multiply that mass number, kilograms, times 9.8. Okay, and that gives me still a small number. Didn't change much in terms of order of magnitude. Now, I am rounding off here, so I will get orders of magnitude rounding error in this. And take note that 1 Newton is equivalent to 1 kilogram per second squared to give us the unit of Newton, because force true gravity essentially is a force. Okay? I have to block this off. You know what? I'm just going to erase that. Bye-bye. Boom. Oop, not all of it's gone. Okay, and next I'll solve for the area. And we also expect the area to be small as well, but this is squared. It's going to be in terms of meters squared, which are indeed is the units for area. I know, I just realized I'm using everything in 3 sig figs, which is a habit, but our answer is going to be in 2 sig figs because all of our given was exactly that. Okay, so now I am all ready to use terminal velocity formula. Okay, and just for redundancy, I'm going to write it all again. This is air, and this is the cross-sectional area. Okay, and just plugging and chugging 2, and I'm going to actually write down the entire units for newtons in this case. kilograms meters per second squared, which is newtons. The drag coefficient does not have any units, times the density does have units, and the area is right above. Meter squared. Now watch what I do with the units. That meter squared cancels out with one of the meters there, so this is just a 1. That kilogram cancels out there, and watch what happens. Essentially I get meters per second squared and a 1 over meter here. Now what happens is that I take the reciprocal of that and I get meters per second squared times 1. You have to be careful because this is going to give me, just multiply across, meter squared and second squared. And that's all good because all of this is underneath a square root, which gives us exactly units for terminal velocity. It gives us meters per seconds. There we go. The units should all work out. And just go ahead and plug that into a calculator and you'll see that you get something approximately 7.4 meters per second. Or that is also close to 17 miles per hour. Now if you're driving like this on a highway, I think the cops will and should stop you. That is way too slow. That's if you're going through a parking lot or something like that. And this is the speed, the approximate speed at which terminal velocity of a raindrop falling about 1,200 meters and a diameter or radius of 1.5 millimeter. Now this is not fast at all. It's really, really slow. So you can imagine the impact of that on anything, any object, wouldn't leave that much of a force or impulse on it. Wouldn't take that much to actually stop a raindrop, which is good, because here is the other case. In the other case of, and this doesn't take that long to do, free fall, as discovered by Galileo. And remember that it is explained by Newton's second law. Now I'm going to go ahead and break down delta y into y final minus y initial, because check this out, our y final is actually 0 meters on the ground, and what's going to happen is I have a negative there and a negative there, which results in a positive, and that's good because we're underneath the square root. We don't want that to happen. Okay, so that results simply in 2 times 9.8 times our initial height. And take note that our units also resolve as well. You have meters second squared times meters essentially over 1, and I get meter squared second squared, the same thing that I got above. Okay, but the number, the magnitude this time, whoa, is going to be a whopping 153 meters per second. Now to put that in perspective, that is approximately equal to 340 miles per hour. Okay? If there was no air resistance, imagine a million thousands of raindrops falling at that speed. That is no fun at all. That is a disaster movie waiting to happen. Okay, because you can see the difference on when there is air resistance, that is the speed, and when there isn't. Okay, of course, the case for real life is when there is terminal velocity, when rain, as soon as it's precipitated, will reach terminal velocity within several meters. Okay, just imagine if there wasn't. Okay, I hope you enjoyed, that you can understand what's going on here. Remember, don't forget your free body diagrams there as well. Okay, enjoy.